snowballs around. You can make snow angels, as I just did outside Con Hall here. This is me. You can go sledding. So the best sledding hill in Toronto is Riverdale Park. So if you go to get your sled and go to Broadview subway station and walk maybe about 2 blocks south on Broadview, you will see the best sledding hill in Toronto. It's really, really awesome. Long way, and then a big sort of flat part at the end, and you don't even end up in the river, Don River. I mean, there's just so much. You can build like snow forts, and 2 forts have a snowball war. I remember when I was a kid, the snowplow used to, for some reason, dump a giant pile of snow in my front yard. So of course, we would dig tunnels in it, and I remember pretty much every winter we would end up with a kind of like a big fort inside this big pile of snow, and just spend all kinds of time in there like little subterranean critters. So kids love snow, and so it's important for you to be immature at this time of year and play around in the snow if you get a chance. Okay, so chapter 9 of your e-text opens up with this photo. This is talking about pulsars. So what a pulsar is it's a star, which was a hydrogen-burning main sequence star for a short time, but then used up all its hydrogen, collapsed down, used up all its helium, collapsed down even further, and when a lot of mass that might be rotating collapses down, it rotates faster as all that mass gets closer to the rotation axis and conserves angular momentum. And so if a star collapses down to a neutron star, it's often rotating very rapidly, and if it has a magnetic field axis, which is not aligned with its rotation axis, then it sweeps around in a big circle and it can emit radio waves by a synchrotron radiation along the magnetic pole, and you observe it as a pulsar. So it's a nice photo, and they talk about this giant radio observatory, but this isn't the one. This is down in Arizona. This is just a misleading picture in your book. This is the actual big giant radio telescope that Jocelyn Bell built as a grad student with chicken wire or something in a big field outside of Cambridge, and she then used it to observe radio sources and was able to find a very, very rapidly oscillating source, which was originally very mysterious. No one had seen anything like this. This was the first pulsar discovered, and it was thought maybe it was alien signals or something, but it turned out to be a natural source. And then, as a direct result, her thesis supervisor, Anthony Hewish, won the Nobel Prize for, quote, his decisive role in discovery of pulsars, which is basically having Jocelyn Bell as a grad student. So that's kind of how sexism works in science sometimes. Very controversial and badly awarded Nobel Prize. I've got Sophie, do you see anything on the discussion board yet, or not yet? I'll keep an eye on you though. Just let me know. And if anyone wants to shout out as well, you can as well. I'm going to be asking for some more volunteers because we've got a couple of blanks coming up, but it looks like, well, actually even Friday, I think we'll have a blank, but maybe Andrea can fill in. Oh yeah, so I did post the test 2 solutions if you're curious. You want to look at that. I'm not going to go over it today, just because I find it, not everyone wants to go over these things right after the test. But if you do, there's a whole 45-minute YouTube video of me going through it and solving it out. So you can go through there. April Seeley is working as fast as she can right now to scan the multiple choice part of the test. I don't know when she will be done, but I would not be surprised if it's done by the end of today. In which case, you will receive a mark of 20 from gradescope.ca just for that part. But keep in mind, the test is at 28, and you'll have to wait maybe about 2 weeks for the remaining 8 points. We just wanted to give you a bit of a heads up so that you know what you got on the multiple choice part of it. Does that sound okay? And unlike test 1, there's no bonus point for following instructions. Okay. I think that's all. And anything of note on our discussion board? Looks like we're good. Everybody's good? Should we go on to chapter 9? Okay. So if you've got, my daughter actually has a record player, a turntable in her room where she listens to Taylor Swift. But you've got a horizontal disc that's rotating around, kind of like a record player or something, and you're looking down on it from above. And so this is from your text. There are coins. These are called pennies, actually. I don't know, they're kind of old-fashioned. They still have them in the United States. And they are rotating around. So what she does is think about the speed of the coins as the whole turntable moves around. Well, if you were to put a coin right on the rotation axis at the very center, it wouldn't move at all. It would just sort of sit there and spin. But as it gets farther away from the rotation axis, it'll go a little bit slow and then a little faster. So this tangential speed gets faster and faster as it gets towards the edge. And the way you can think of that is almost with this kind of arc length philosophy. You've got the same angle being swept out or something in the same amount of time, no matter where on the disk the coin sits. So if there's an x-axis here and you do t and then t plus delta t, everything moves the same angle as measured from the vertex, which is the center of the rotation axis, which comes out of the page in this case. So it's an angle. Basic idea is that there's similarities between motions of different points on a rotating rigid body, and that is during a particular time interval, all coins at the different points on the rotating disk turn through the same angle. So the textbook postulates perhaps we should describe the rotational position of a rigid body using an angle. And this is where they, for some reason, have chosen to use radians instead of degrees, but it's okay. I think you could use degrees, but you would have a 180 over pi in all your equations, and so they just try to simplify it a little bit by just changing the unit. So I guess the SI unit of angle is really the radian. So here's your equation for arc length S. It's r, which is this constant radius, times theta, if theta is in radians. And we kind of went through this before when I was introducing chapter 8, so I won't spend too much time on it, but the idea is that now that you have a theta, you can do the rate of change of theta. If you were to make a plot or something of theta versus time, and it looked like this or something, then if you were to find a slope, then the slope, whatever that would be a plot of omega versus time. So it's either a time derivative or a limit or something. It's the change in theta divided by the change in time. And there's this equation which kind of looks like, I guess, recall. Do you remember for kinematics we had that x final equals x initial plus v sub x times t, or delta t or something? Put a delta there. This is a very similar looking equation. It's got, instead of x, it's got thetas, and instead of v, it's got these omegas. So yeah, by the way, this thing is called an omega. Looks like a W, but you're not supposed to type a W on MyLab and mastering, or it'll tell you. The answer does not depend on W. Okay, let's do a question based on this idea. So here we have a vertical circular motion. It's a Ferris wheel, and this is a special Ferris wheel where you can choose if you want to sit on an inner car, there's 4 of these inner cars, or one of the outer cars. So it's saying, compared with the seats on the outside, if you're on one of these, the one in the circle, the middle one, the inner cars have A, smaller angular speed and greater tangential speed, B, greater, I'll just let you read through that. And I'll maybe give you a minute to think about this. Pair up, share your answer, try to think about what's the difference between angular speed in radians per second and tangential speed in meters per second. We've been working with just regular speed, tangential speed, for this whole course up until now in meters per second. Now we've got this new thing, radians per second. So I'll give you a minute. Think, pair, share, please. Timer. Okay. You got an idea? We have 280 responses to 293. Give you 5 seconds and then we'll discuss. Going once, going twice, and stop. HDMI is fixed now. So we've got 80% of you voting for C, which was they have the same angular speed, but a smaller tangential speed. That's what I like. So the idea being, it doesn't matter where you are on a rotating rigid body, everywhere sweeps out the same angle per time. So it's always the same omega. So omega is constant everywhere. What's different is that V. So I will just say that, maybe let's put some notes here. V is the tangential speed, and the units of this are meters per second, and omega is the angular speed, and the unit of this is radians per second. And V is equal to omega R, and omega is the same for all points on the Ferris wheel, all points on a rotating rigid body. Rotating. So why then do points on the outside move faster than points on the inside? That's because R changes. If R is 0, then it's not moving at all. If R is way out on the edge, then it's moving faster and faster. Sound good? Okay. So, angular velocity, omega, is the rate of change of angular position, radians per second. The other thing that can happen here is you can change omega. So, where's my wheel? Did you bring? Oh, it's right here. It's all set up. So I've got a wheel. So idea being, if I start this thing rotating at some It tends to want to go at a constant omega. Maybe it slows down gradually. But I can change omega, right, by applying a torque and speeding it up or something. So that's alpha. It's not an A, it's the Greek letter alpha. Radians per second squared. So it means radians per second, but per second. Exactly analogous to how meters per second goes to meters per second squared for regular acceleration. But this, again, is something that's going to be similar for all points on the object. They're sweeping out the same angle in some amount of time, so doesn't matter how far you are from the rotation axis, you're going to have the same omega, same alpha, and the same, I guess, theta. And if you were to make some plots, I guess, so another question someone asked. When objects are rotating, can we still model them as point-like objects, which we've been doing up until, I think, chapter 7? No. No more point-like objects. Starting with chapter 8 and chapter 9, the idea is that these are no longer, you can't model it as a point-like object. You model it as a bigger object, and you have to do these extended force diagrams, and it's a collection of particles all at different distances from a rotation axis. So. But I guess there are points on it. Very good. Any actual questions? No? Yeah, you, please.
Like for the tangential acceleration,
yeah.
How can we like convert the angular velocity to tangential velocity?
The angular velocity to so I've got some equations for it. Actually, let's do it right here. So the tangential velocity is omega, which is the angular velocity times r, and then the tangential acceleration is the angular acceleration times r. Does that help? These are your three kind of conversion equations right here. Does that help?
But how do we convert, like, how come we can come up with this equation?
Well, I just wrote them down. So these are just derivatives of, these are just slopes. The omega is the slope of theta. So what you got to remember, what's going on here is you've got in these graphs, so what is going on? You have theta, which starts at 0. It's the position of this orange piece of tape. So it goes up and then stops, I guess. That's the motion we're trying to describe. Why did it do it? I don't know, maybe because I moved it. But what happens is that first the omega speeds up and then it slows down and stops. So that's the omega part, the green curve. And then another, the orange curve is that there's some positive acceleration and then negative acceleration. And it stops. Okay? So you're describing a particular motion. So this is what is called rotational kinematics. We are just describing how something moves around. We haven't yet gotten onto rotational dynamics, which is where then we use torques and figure out why it's moving like it is. Okay? Very similar. This whole thing is analogous to how we started the whole course, but that was with linear motion in meters, right? This is now with just rotational motion in radians. But similar stuff. Those are great questions, thank you. Let me know if you have anything else. If you got the microphone, you're completely in charge of whatever you want to ask. All right. Great. There's some signs, so let's go through those. I don't know if you want to stare at this for a while, but so it's pretty straightforward. Basically, it's very similar to, do you remember when we had those carts? I said, is it possible for something to have like a positive velocity but a negative acceleration, or maybe a negative velocity but a positive acceleration, and what does it all mean? It was that if the acceleration and the velocity are in the same direction, either both positive or both negative, then the object is speeding up. But if the acceleration and the velocity are in opposite directions, whether like that or like that, plus minus or minus plus, then the object is slowing down. And it's the exact same deal with these signs. So if omega and alpha have the same sign, then you would say that the rotation speed or something like that is speeding up. Rotation speed is increasing. So that would be the case where you've got like speeding up counterclockwise or speeding up clockwise, both negative or both positive. But if omega and alpha have opposite signs, then rotation speed is decreasing. It's decreasing. So it's good to, it's almost a bit of review, but it's kind of different when things are rotating, right? Should we do some learning catalytics with these? Let's do this one. Let's do two of these. So this is a little picture showing the motion of the fan, how it's moving. And you also have the information that it's speeding up. So if it's rotating here, which it is, its rotational speed will increase. So in this, what's the omegas and the alphas? I'll give you a minute to think, pair up with a neighbor, find a neighbor. Unless you don't have a neighbor, share your answer.
Professor, there's a question about the fridge tipping last lecture.
Fridge tipping. Oh yeah, we were going to do that, weren't we?
So it says, could you please explain how to do those questions? And because last class we skipped a question about fridge angle tipping.
Yeah. I totally forgot. Can I do it Friday? Because I just don't have it in my slides. But thank you very much to whoever put that on discussion board. I totally forgot to do the fridge tipping question, which is more like a chapter 8, but it's good to review that because it might be on the final exam. So. How's it going with this question? Should we 5 seconds, please, to click in? Going once, going twice. Got 301 responses. So 86% of you are liking D, that omega's negative and alpha's negative. So yeah, so it's clockwise. So that's the idea, is that since this is clockwise, that's the motion, clockwise motion or something like that. So that means that omega is negative. And then the fact that it's speeding up means that alpha has the same sign. Speeding up means alpha has the same sign. So it's also negative as omega. That's my reasoning. So I like D. That's good. I'll do another one. Just real quick. This one I really will give you 1 minute. 10 seconds. And going once, going twice. You guys getting it? 92% of you voted for B, which is the answer I like as well. In this case, it's rotating counterclockwise. That means omega is positive, but it says that it's slowing down, which means alpha has opposite sign. So alpha must be the negative one. So I like B. All right, what's next? Okay. So this is I'm going to make a little chart of analogies here, but linear kinematics has position measured in meters, velocity measured in meters per second. That's just the slope of whatever position versus time graph that you have. So rise over run, meters divided by seconds. And acceleration, linear, a sub x, is the slope of the Vx graph. So the rise now is in meters per second, and the run is still in seconds. So it's meters per second, or meters per second squared. Rotational analogy, theta is the angular position now in radians. And the definition of a radian is that 2 pi is the full circle. Angular velocity is the slope of position versus time graph. So rise being, Sophie, maybe is your microphone on? Do you want to turn it off? You've got rise in radians, run in seconds. So you've got radians per second is your angular velocity, and the angular acceleration is the slope of that omega versus time graph. So you got radians per second is the rise, divided by seconds is the run. Radians per second squared. And what's interesting is that this is a little magical leprechaun. It's the magical unit. So the units check, if you've noticed, doesn't really work. So look at the units of this equation. You have Vt, that's in meters per second. Vt has units of meters per second. So that should be the same as the units on the right-hand side of the equation, right? But omega times r, you have radians per second times meters. R is in meters. So this should be radians meters per second. So that's not the same as meters per second. So the way we solve this in physics is we cross out the radians. And then it's just meters per second. All right, so not only you shouldn't just cross out your units and forget about it, but this is the thing. Radians are the magical unit in which you're allowed to just pop them in there or pop them out of there at your own will. And it's because they are dimensionless, I guess. Meaning that it doesn't have dimension of length or mass or something like that. Yes, your question? Meter per meter. Yeah, it's something like, how much arc length is there per radius of the circle or something like that. So that's a good way of putting it. So radians appear and disappear as they please in your equations. So don't be disturbed when they do that. You should be disturbed if meters appear or disappear in your equations. That shouldn't happen. Or if a kilogram suddenly shows up there, you better worry about that. But if a radian sneaks in there, a radian leaves, don't even worry about it. It's okay. So because it's the magical unit. All right. Hey, do you remember all those equations of kinematics from before? It's a bit blurry. Wasn't there another one that I had? I think I had a fourth one somewhere. This is just from your table. But it was something like V1 or V plus V0 over 2, something like that, equals x over t. Remember that one? Something like that. So you would have that omega plus omega 0 over 2 equals theta over t, something like that. Theta, maybe theta minus theta 0. Something like that. That'd be your fourth little kinematics equation. But all the kinematics equations have their analogies in rotation. You just go to Greek. All the x's change to thetas, all the v's change to omegas, all the a's change to alphas, and you can use the exact same equations over again. You can just rewrite them out. And I can give you an example of actually doing this, what happens. Want to do one? I'll show you what I mean. A bicycle wheel has an initial angular velocity of 150 radians per second. So I write that as omega 0 equals 150. Oh, sorry, 1.5, 0 rad per second. And a constant angular acceleration of 0.200 radians per second. So alpha is constant. So you can use the equations of constant acceleration. Alpha is 0.2 radians per second squared. Through what angle has the wheel turned between t equals 0 and t equals 2.5 seconds? So this is your sketch. You've got a wheel, and it's turning around some angle, theta. So this, from here to here, has some angle theta, where theta is 0 equals 0 or something. Make sense? And then you just use, I'll just note that I don't care about omega final velocity. Well, sorry, I should say final angular velocity, right? Or rotational velocity. So we'll use, let's just go back a slide one sec here. The one where you don't care about the final is 9.6. Use equation 9.6, which is that theta is equal to theta 0 plus omega 0 times t plus 1/2 alpha t squared. So the t stays the same, everything else shifts to Greek letters. We're going to assume that theta 0 equals 0 at t equals 0, and theta is equal to 0 plus 1.5 times 2.5 plus 1/2 0.2 times 2.5 squared. And I get 4.37. But what are the units? Anyone know? Radians. Good. And that's it. You didn't actually even have to use radian mode on your calculator because you didn't press the sine button or the cos button. Just know that it's radians. And that's less than a full circle. I think that 2 pi is about 6 radians. So is a full circle. So the wheel rotates less than once around. Okay. What time is it? We're good. All right, and then we've already gone through this a lot, but let me just talk a little bit about the rolling without skidding. So if you have something that is rotating counterclockwise and it's rolling without slipping on the floor, it can move towards the left, I guess, if the bottom point stays stationary. So that's called rolling without slipping. And what's interesting is that as you sweep out, say, a whole 2 pi radians, then the object moves the circumference of the circle, right? Whatever the axle here moves a distance which is equal to the whole circumference of the circle when it rotates through 2 pi radians. So these equations actually give you the position or distance or something like that of a car that's rolling without slipping or whatever, or of a cylinder that's rolling without slipping. So these equations that I had from tangential, all that tangential speeds and stuff because we were assuming, I guess, that if the axle is stationary, then these are tangential speeds. Those get converted into the speed of the center of mass of an object that's rolling. So the distance it goes is theta times the radius of the object, which I'm using capital R now because it's like a fixed number, radius of the wheel. And the speed is omega times capital R, and then the acceleration of the car would be alpha times the capital R. So these same exact equations, but now you're talking about rolling without skidding. All right, so my next thing on this list is rotational dynamics. So in order to do that, we have to think about rotational inertia, which is the analogy of mass. So remember this equation? This is how I remember I used to write, every once in a while I've done this for Newton's second law, which is that instead of writing F equals ma, you can write A is equal to F over m. The purpose of writing it that way is kind of cause and effect. The cause of an acceleration is a force and a mass. The bigger the force, the more it'll accelerate. But the bigger the mass, because it's on the denominator, the less it'll accelerate. So there's a whole analogous issue going on with rotation, which is that the rotational acceleration will be bigger the more torque there is on it, but it'll be less the more the rotational inertia. Instead of mass, we have this thing called rotational inertia. And we can, is it aux plate? Yeah. Oh, actually, I need this little pen. Are you able to do something about that? Okay. So what we have here is an object with 2 masses on it, and if I wanted to rotate it, I would apply a torque. So I could apply a counterclockwise torque by pushing it this direction. I could push it like sort of to the left at the top, or I could even slow it down, put a clockwise torque and sort of slow it down with my pen. And it's a little hard to do it. I push it with a sort of a little force, it goes slightly faster and faster and faster and faster and faster. Okay. But I can now change the rotational inertia of this object by changing the location of the masses. I put them right towards the center, then all of a sudden, it's like very, very easy to spin it up with my pen. Okay, because the mass is all concentrated towards the center, and it just goes back and forth very easily. It's like almost like a little plastic fan or something like that. But I put the masses out here, very, very different feel to it. Now it's, ow! Now it's really, it wants to keep rotating once it's going, and it's harder to get it going. So you kind of have to play around with it to really you need a whole bunch of these in practicals or something like that to really believe me, but you got to believe me. It's harder to accelerate, to change its angular velocity when the masses are out far than it is when the masses are close to the middle. So there's this new concept called rotational inertia, which has to do with the mass, for sure, but it also has to do with the location of the masses. So consider a body made of n particles, each of mass m sub I, where I equals 1 through n. Each particle is located at a distance r sub I from the rotation axis. For this body, made of some countable number of particles, it's the sum of all the masses times their distance from the rotation axis squared. Okay. And there's Often two particles. So, i.e., if n equals 2, then the rotational inertia is m1 times r1 squared plus m2 times r2 squared, for example. So, you need to define a rotation axis first. Similar, I guess, to maybe center of mass. You always have to define where x equals 0, right? When you're doing those center of mass equations, it's sort of a similar thing. Define a rotation axis, then you've got r for all the particles, and then you know their masses, and just sum these things up. Let's do learning catalytics first, and then I'll do a couple examples, and then we'll be done. So here is something very similar to this, a dumbbell, but one of them has twice the mass. So dumbbell A has twice the mass as dumbbell B. So maybe you've got 2m for dumbbell A, but dumbbell B has m over 2 and m over 2, so it's half the mass. But dumbbell B is twice as big. So remember, the more mass something has, the more rotational inertia, but also the farther apart the masses are from the rotation axis, which is about the midpoint in both cases, the greater the rotational inertia as well. So how do these things, if they cancel out or whatever, try to think about it. Think up, pair, share. It's either A, B, or they're the same. Give you a minute. Okay. Right. So maybe click in an answer or guess. Going once, going twice. People seem to be saying, and I was hearing some conversations in the front row, a lot of people are voting for B here, which is the one that I like. It's not obvious, this one, which is, I think what you have to do is actually just work it out. So I think that I sub A is going to be mass 1, which is just m, I guess, times r over 2 squared, plus mass 2, which is also m, times r over 2 squared. So it's, if you do that all, there's r squared over 4, you get mr squared over 4 plus mr squared over 4. I think you just get 1/2 m times r squared. And then if you do IB, it's m over 2 times r squared plus m over 2 times r squared, and you get mr squared, which is greater than 1/2 mr squared. I think that's pretty much the only way you can solve this out. You have to solve it. The other way of thinking of it is that, yeah, it's true that as radius goes up, it increases. As mass goes down, it decreases, but the radius is sort of more important than the mass because it's squared. So doubling the radius increases the rotational inertia by a factor of 4. But having the mass only decreases the rotational inertia by a factor of 2. And so the radius is more important than the mass in this case. I'll do a couple of quick examples and then you'll be good to go. And I will do this refrigerator on Friday, I promise, thanks to whoever put that in the thing. 4 small metal spheres, each with a mass of 0.2 kilograms, are arranged in a square 0.4 meters on a side and connected by extremely light rods. I'll just sketch it again here. You've got M and M and M and M. And you've got a rotation axis in the middle, which goes around like that. And this distance here, which I'll call x, is equal to 0.4 meters. And the mass, m, of all of them is 0.2 kilograms. You are asked to find the rotational inertia. So I think to diagram this out, I need the radius. That's the question, right? So if I have like R2 or something, and this is 0.2, if this is 0.1 and 2 and 3 and 4, I could label them if I wanted to. They're all the same, but this would be x over 2 would be this distance from here to here, and I think that sort of by Pythagoras, I think that r squared equals x over 2 squared plus x over 2 squared, because it's a sort of a 45-45 triangle. Make sense? So basically r squared equals 0.4 squared. Anyways, so I is equal to m1 r1 squared plus m2 times r2 squared plus da da da. It's 4 mr squared. So I is equal to 4 times 0.2 times 0.08. So I got I is equal to 0.064 kilograms meters squared. So there is a unit to rotational inertia. It's kilograms times meters squared. Again, coming from that equation, you've got the mass of each particle times its distance from a rotation axis squared. So what's interesting about rotational inertia is that it actually depends on where the axis is as well. So here's an example where the thing is rotating about an axis that's coming out of the page. Well, what if you choose a different axis? You get a different rotational inertia. So I'll just do real quick. What if the axis was like this, and it's kind of flipping in and out of the page? Then what you've got is now these distances are different. Here's 1, here's 2, here's 3, and here's 4. Now the radius is x over 2. You don't have to use Pythagoras now. So I is equal to 4mr squared. I just equals to 4 times 0.2 kilograms times 0.2 squared. So now you get I is equal to 0.5 as much, 0.032 kilograms meters squared. So this is half as much as when the rotation axis was perpendicular to the plane. When the rotation axis is in the plane, then these objects are closer to the rotation axis in the plane. Closer than when the rotation axis is perpendicular to the plane. Okay. So I guess we'll talk about this a little bit more next time, but there are these kinematics equations that are analogous. There's also an analogous Newton's second law, and I'll talk about that more on Friday. Newton's second law for rotational motion. And something to think about, remember this whole pulley question? We always assumed the pulley was massless and frictionless. What if the pulley does have mass? In that case, is the tension T1 equal to T2? I'll answer that for you on Friday, and I'll do the fridge tipping question as well.